I thought this was kind of a neat photograph, and so I thought I would use it to talk about the connection between linear and angular speed. Of course, all these quantities are related. Um, Now we're talking about a specific case when something is rolling along the ground. If we imagine this wheel just out in space and it was spinning around, we would say it has an angular acceleration. And we could talk about any points on the wheel, on the rim of the wheel, having a linear speed as well. But we're talking about now something that's rolling. So we're imagining the entire bike is moving forward at some speed, v naught. So we could represent that with these red arrows here, that every part of this bike is moving to the left at that speed, v naught. For this to happen, of course, the bike has to be spinning, the wheels of the bike has to be spinning, and so the tangential speed of any point on the wheel has to be, v sub t has to equal to v naught. Because remember that s is equal to r theta, and we only make progress forward if s is increasing, and we'll only make that progress forward if theta is increasing, or in other words, there's an angular velocity omega. If we were to draw that tangential speed because of the wheel spinning, it would be to the left here for the top of the wheel, and it would be to the right here for the bottom of the wheel, because those velocity vectors really represent where is the point on the wheel rim actually moving. Now notice if we talked about the total velocity of any point on the wheel, this gets kind of complicated because it's the sum of these two things. At the very top of the wheel, the total velocity is going to equal that velocity of motion v naught plus that tangential speed velocity v sub t. And at the bottom of the wheel, those two things are acting in opposite directions. At the center of the wheel, there is no some v sub t because it's the center of the wheel. There's no radius there. So the total velocity is just v naught. So the interesting thing is that the wheel velocity at the rim is actually twice as big at the top as it is at the middle, and it's at this instant in time 0 at the very bottom of the wheel, because we're talking about a situation where the wheel is rolling. And when this person snapped a picture of this bicycle whizzing on by, notice that the spokes at the bottom of the wheel are actually visible in the picture because they were temporarily still. At the very top of the picture, the wheel rim is moving so fast that the spokes are a blur. You can't see them very clearly. This all comes about because of the idea of the fact that the wheel is rolling. If the object was just out in space, this wheel was imaginarily spinning out in outer space and not moving past us, then we wouldn't have quite the same condition because it's not the center of gravity of the whole wheel moving on by at speed v naught that's happening. It's just an object sitting out in space, spinning away. But the act of rolling without slipping does a slightly funny thing.